Thank you. Big thank you to the organizers, Colin, Avishai, Joel. It's wonderful to be back here. I think we're all enjoying this in-person meeting. I know I am. So we've got quite a lot of ground to cover. Until last week, I was not going to say anything about James Webb, but we learned a surprising amount in just a month from the Sears data. So I can't help myself. And yeah, I wouldn't show it if I didn't believe it. So I don't think we have done quite enough of this. Start at CANDELS wavelength at redshift 2. These are the two most massive galaxies in the Sears footprint. Before I continue, big thank you to Steve Finkelstein and his team for putting together such a wonderful ERS program that's going to tell us about everything, all the modes of James Webb. All I'm going to talk about here is NIRCam imaging. So these are the two most massive star-forming galaxies at redshift 2 in the Sears footprint, seen at sort of CANDELS wavelength here. It's a bit messy, you know, UV, rest frame UV. Then you go to the longest wavelength, and things really change, right? And then, of course, you can make, it's scientifically useless, but you can make these color pictures, and you can start seeing what's going on. I'll take one more step, running some deconvolution algorithm, because we know the PSF pretty well, and that really brings out even more of the structure. So what we see here, the very first galaxy I looked at has this giant bar. I assume that's going to be rare, but who knows, right? It's beautiful ring, spiral type structure. You see the dust lanes. The galaxy at the bottom is equally massive, more inclined disk, probably. But, you know, this is what James Webb really adds to the picture, of course. We know it on paper, but to see it like this, I was really, yeah, almost blown away by the galaxy at the top in particular. I have to say, I'm not part of the Sears team. There's a group of people, mostly in my own academic family, that jumped at the opportunity to get their hands dirty with these new data. So there's some data wizards like Gabe Brammer and Ivo Labbé who really yeah, created their own mosaics, and that's the version of the data I'll be working with. So here are the 6 galaxies in that mass range, in that redshift range, sorted by their specific star formation rate. The specific star formation rate and masses, by the way, come from the CANDELS analysis of the CANDELS data and the multi-wavelength stuff. Nothing to do with Sears or James Webb. This is CANDELS-based physical parameters and NIRCam pictures. So you can see in this mass bin and also in the lower mass bin, so more like a little bit below L star, this correlation between galaxy structure and star formation activity, right? And NIRCam shows the same thing as WFC3 did. Large extended objects forming stars, more compact, centrally concentrated things not forming stars. It's a good thing to check, right? That's why we built a machine from the redshift 2 perspective. Just to keep ourselves honest, this is the most massive galaxy in the footprint at this redshift. It doesn't seem to really follow that pattern, right? So let's not, I think about galaxy formation very schematically, and I know many of us do, and this should keep us honest, right? This is a 80 kiloparsec thing. The dynamical timescale is probably a gigayear, so this is another short merger phase we're looking at. This is the main formation epoch of this giant galaxy, and you know, it clearly doesn't fit in a neat picture of, oh, there's star formation at disk, you have a compaction and an elliptical. This should keep us honest. We should always keep this in mind. You see the low surface brightness stuff is even here if you look at the screen. And it's blue, it's unobscured, and there's dust lanes. It's a pretty crazy object. So we already did some actual science with these images, more than just taking pictures. This is a paper by Ranzis, with the same people. I'm a co-author on it now as well. Because from the size evolution perspective, the first thing we'd like to know is, are the galaxies smaller at the long wavelength or not compared to the CANDELS wavelength? Right, and what we see here is in 3 redshift bins, as a function of the stellar mass. Again, that's CANDELS information based, right? Only that axis comes from NIRCam. That's the ratio of the 4.4 micron size and the 1.5 micron size, an observed frame. So the longest wavelength compared with the longest CANDELS wavelength, essentially. And what you see that above 10 to the 10 solar masses, indeed the rest frame near-infrared sizes, the 4.4 micron sizes, are 0.15 dex-ish smaller than the shorter wavelength sizes. At low mass, that effect goes away, so what you see there in CANDELS in the rest frame blue is what you get at longer wavelengths as well, from the size perspective. Right, and that size difference that happens for star-forming galaxies, passive galaxies, that's the red and blue data points. It happens at all redshifts by about the same amount. Pretty regular pattern. Now this was a very quick job, but not a dirty job, because we put a lot of effort in understanding the noise properties in the PSF as well as we can at this point. The only dirty part is these outliers that were not examined very properly. What's going on? Is it something technical? Are they weird galaxies? Is it segmentation? Don't focus on that. Focus on the bulk of the data points. Okay, does any of this have any bearing on the size evolution picture that we've learned from CANDELS? So in this is all CANDELS now, no NIRCam, right? This is old stuff, 2014. So this is the size evolution picture we've developed from CANDELS. You see the quiescent galaxies evolving steeply in size, but the slope of the size-mass relation stays constant, the scatter stays constant. Star-forming galaxies have a flatter slope, they also get smaller. It's kind of summarized in this panel here, where that's the intercept of the size-mass relation that evolves very steeply for the quiescent galaxies and less steeply but still significantly for the star-forming galaxies. So how does this change with these new James Webb data? Let's take it one step at a time. I should have removed these first panels. This is now Sears data, where we do a similar exercise using CANDELS-based masses, and we plug in a series of different sizes. For starters, the HST sizes themselves of the Sears sample. Remember, CANDELS is a big survey, Sears is a small part of it. So these are HST CANDELS sizes for the Sears footprint. And you basically confirm that you see the same picture as in the entire galaxy, in the entire CANDELS survey. Yeah, no real difference. So now we replace the HST sizes with the Sears sizes, but at the same rest frame wavelength. It looks a little different. I'm a bit annoyed by that because it should just be the same, because the size measurements themselves agree very well. I don't quite understand. It's under construction, but the basic picture is the same. Fast evolution, slower evolution, both very significant. Now on the right-hand side is the most interesting one that we're after, rest frame 1.2 micron, right? And again, we see a very similar picture. Strong size evolution for the early type galaxies or the quiescent galaxies, and the star-forming galaxies a bit slower. Don't pin me down on the exact numbers there. They're very small on purpose. They could go from minus 1.5 to minus 1.3, I don't know. What I want to emphasize now, and what I believe to be true, is that the general picture doesn't change when you go from the rest frame optical to the rest frame near-infrared. So what does it mean for our understanding of size evolution? I mean, light-weighted sizes are a biased tracer of the mass, of course. So what we really want is stellar mass maps, stellar mass-weighted sizes. Now we believe that the rest frame near-infrared sort of traces the stellar mass pretty well. Right, that's the entire thinking behind going to longer and longer wavelengths. So let's try to connect the dots here. We have our own approach to measuring mass-weighted sizes that builds on work of the past decades. I'm not going to explain it in detail, there's no time. You have to take my word for it. What we measure is, we now switch back to CANDELS, right? This is not James Webb analysis. We go back to CANDELS. So we have these multi-filter Sersic profile fits, right? Which gives you color gradients. And you can convert these color gradients into mass-to-light ratio gradients, which allows you to convert a light map into a stellar mass map. That's the essence of it. A lot of work has been done before this. What we do add is propagation of all uncertainties. That's important. The other thing that's not so important for this talk, but it's interesting, we have a way of deprojecting the profiles to 3D. That facilitates comparison with simulations, of course, and it's a more physical measure of a galaxy size. Not going to talk about it a lot, but it's part of the whole scheme. ask me if you want to know more about our method. The essence is we convert color gradients into mass-light ratio gradients to get mass maps. So let's now go back to comparing seers and candles. So we now have the light profiles from seers, right, at different wavelengths, and the mass profiles I've derived from candles. So this sample here is, again, the overlap between seers and candles. Not that many galaxies, but plenty to see what's going on. This is a comparison of the seers rest frame optical sizes and our mass-weighted sizes. Right? And as people have shown before, the light-weighted sizes are 0.15 times larger. There's discussion in the literature about the redshift dependence of this trend. There's a huge scatter here. I'm not answering these questions per se here, but this is what we get. Now we're going to go to longer and longer wavelengths from seers, so from 0.5 micron to 1 micron, 1.2, and 1.5. So now we've arrived at the point where indeed you confirm this idea that the rest frame near-infrared traces the stellar mass distribution. Actually, I would turn it around and say our mass-weighted size estimates are robust because we produce the rest frame near-infrared sizes, right? That's the right conclusion from this exercise. And the other thing you see when you compare rest frame optical and rest frame near-infrared is that the whole thing tightened. That tells me that we didn't add noise by converting to mass profiles by blowing up uncertainties. We're doing something right, and we get closer to the true underlying mass distribution of the galaxies. Okay. So now we go back to candles, where we have a much larger sample. Here's redshift 1 for practical purposes, just to see what's going on. This is the rest frame optical sizes versus stellar mass, an incarnation of a previous plot. So I should have added the color axis, but it's specific star formation. So these are the passive galaxies, and those are the star-forming galaxies. The lines trace the median and the 16 and 84 percentiles. So this is light-weighted sizes, the ones we've been using for nearly a decade. So now I'm going to replace the light-weighted sizes with our mass-weighted sizes. And you can sort of see how it changes. For most people, this change is not important, right? You say, okay, the basic picture is in place. There's changes in detail. For others, it might be important that the slope is a bit flatter. But what does not happen is that the size difference between the star formers and the non-star formers goes away or anything. Right? What does not happen is that, what also doesn't happen is that low mass, the sizes change, consistent with that constancy with wavelength. I'll go back and forward one more time. Now, last step, we add the deprojection. So now we go to 3D sizes. Sorry, I should have mentioned these sizes I've been talking about are projected sizes on the sky. The galaxies are modeled as an ellipse, and it's the long axis of the ellipse. That's our size here. Now we make it a 3D size, so which sphere contains half of the 3D luminosity distribution? And this is what you get. So from 2D to 3D. Now the slope is a bit steeper again, but compared to the very first one, the whole thing has shifted down a bit. So deprojection does not matter at the high mass end because we're all looking at oblate things, and it doesn't matter how you project them, they always have the same size, and that size happens to agree very well with the 3D size. These galaxies here have strange shapes, so their 3D sizes are a little bit different. I don't want to go into more detail here. Okay, and this is preliminary. I believe it to be true enough to show. Now we're going to measure the size evolution of the quiescent galaxies from our mass-weighted sizes in candles. We're comparing the light with the mass-weighted sizes. So the intercept evolution, the slope evolution, and the intrinsic scatter evolution. I'm going a bit fast here, but we've got lots of ground to cover. No, ask me if you want to know more, but the key point is that the mass-weighted evolution just is the same as the size-weighted evolution, just offset down a bit. Slope and scatter are very similar. You should know that to believe the intrinsic scatter estimate, you have to know your uncertainties really well. I don't know if you do well enough, but these are our best effort. Okay, enough about sizes. We've been talking about sigma 1 as a galaxy evolution driver of some sort. So let's see what happens with that if you go to mass-weighted profiles and deprojecting. It turns out to be important, more important than for the sizes. So here's the specific star formation rate. Again, this is CANDELS, not James Webb. Again, sigma 1 for a sample at redshift 1 at mass 10 to the 11th. This is sort of the trend that drives our thinking, right? If galaxies to the right of the line that are quiescent, by and large, galaxies to the left of the line are star forming. It's a necessary and basically sufficient condition for quiescence. Not quite, but close enough. It informs our thinking. Now, this sigma 1 here is defined as the total stellar mass of the galaxy, and then you take the light profile, right, that's the standard practice, and then you look in a circle with radius 1 kiloparsec. In that light profile, you measure what fraction of light is in there, and that's how you get sigma 1. Right? It's kind of wrong because it's the light profile, it's the mass profile. So the question is what happens if you replace that with the mass profile, because that's what we really want to know. And it kind of gets murky. Right? If this was our initial result about the sigma 1 star formation correlation, we might not have made such a big deal out of it. It's clearly a necessary condition for quiescence, but by and large not sufficient. There's all these star forming galaxies up there. So it doesn't mean that the whole thing falls apart. No, deprojection to the rescue. Because these were projected sigma 1s in the cylinder through the whole galaxy. Those galaxies up there have low Sersic indices, so there's a lot of material along the line of sight that's nowhere near the center. For the high Sersic index galaxies here, that's not the case. What you see in the center is in the center. So now that correlation gets even better, right? But that deprojection is important. But it means that the initial stories we wrote about this are kind of correct by coincidence, by combining two systematic uncertainties that sort of cancel each other out. Got lucky there. I guess the work based on velocity dispersions, and there's a lot there that does not depend on these assumptions. So it's a bit of a crude statement, but clearly deprojection is important when it comes to the interpretation of profiles. Okay, some time left. So we've talked about sizes and the sigma 1s, but clearly these galaxies have other structure, right? And I would say a lot of these are like disks. We talked about high-redshift galaxies being disks or not just 20 minutes ago outside. I think those two up there are disks. I don't know what that is. These are disk-like, at least they're elongated. And even these passive guys, they're flattened, right? And if you see one flat thing and one round thing, you have to assume that they're face on and edge on of the same thing. For a sample of 2, that doesn't work, but for a sample of 1,000, it does work. Okay. So what we really want to know is the dynamical structure of these things. We can't quite do that at redshift 2 with the stars, right? All I'm talking about is the stars. Of course, the beautiful H-alpha work we've been seeing from Symphony and CANDELS 3D has told us a whole lot about the star-forming disks. But now we're talking about the stars. What can we know about the dynamical structure of stars? For that, we need to step down in redshift to redshift 1. I'm going to talk about the LEGA-C spectroscopic survey that was mentioned before the break as well. So this is kind of the second part of the story. Scientifically, it's related. Data-wise, we're changing gears now. So the survey I'm talking about, and I was going to say it in 20 seconds, is this 100-night VLT survey with VIMOS, an instrument that's now decommissioned. And the entire purpose of this survey is to get to the stars at redshift 1. Right, so there are 20-hour integrations, and what you get is the stellar continuum with all the absorption lines. I've even removed the emission lines here. Right? Of course, we use them, but for this plot, I removed them. You see that the old galaxies in red here have a completely different spectrum than the young galaxies. There's a lot of information there. So stellar population, the stellar population story is, we're working on that. It's difficult, I'm not going to talk about that. The other part is dynamics. Right, the line broadening from the motions of the stars you can measure. And what's more, we have some spatial resolution. So here's a HST picture. This is all in the cosmos field, by the way, so we have HST pictures for everything. So here's our little quiescent galaxy, and that's the LEGA-C slit. So we extract the spectrum along the slit and measure the velocity and velocity dispersion along the slit. That's the blue data points and the red data points. And then we built a dynamical model. There's these axisymmetric genes models, nothing super fancy, but it does the job for our data. So that means you combine the sigma and the V into a VRMS That's what you combined with the light profile you built a model on. That's the black line. But that's the convolved model. The C-ing convolution is enormous for our data. So the intrinsic model is the dashed line. Then you can decompose that into the rotation and the velocity dispersion component. And what you get is the intrinsic rotation curve and the intrinsic dispersion curve. And with that, we constrain the mass within 1 RE, 2 RE, entire mass profile really, don't really resolve it. So, plus the dynamical structure. The V over sigma we've been mentioning several times. In this case, it's about unity. Apparently all galaxies have V over sigma of about unity. Now this is a quiescent galaxy that is clearly flat and rotating at a decent speed. We know about fast rotators in the local universe, of course, so we can connect those dots. I just want to say first that this galaxy is nothing special. This is all the quiescent galaxies in LEGA-C for which we have dynamical models. So the V over sigma is a function of the dynamical mass. That's the galaxy I just showed, sort of middle of the pack. There's plenty of galaxies with V over sigma 1.5, even 2. Yes, there's a whole bunch of galaxies without much rotation, slow rotators and whatnot. But this is the V over sigma distribution at redshift 0.8. How does this compare with the star formation population? So this is the star forming galaxies in LEGA-C with similar dynamical models, stellar dynamical models. And you can see that, yes, it's different. It's shifted up, but there's also a whole lot of overlap. Yes, Reinhard.
How is sigma measured?
Yes. Sorry. The V is measured at the effective radius of the edge-on model. The sigma is the light-weighted average within the face-on model within.
Which, as you know, is not what we're seeing on the right side. On the right side, we have subtractive rotation.
No. This is LEGA-C.
Oh, it's LEGA-C.
Yes. Yeah. I agree those definitions matter a lot when you quantitatively compare. These are both LEGA-C samples. I guess it's my history that people think that we only look at early type galaxies, fundamental plane evolution and all that. But there's just as many star-forming galaxies in LEGA-C as quiescent galaxies. It's a blind K-band selected sample. We just sweep everything up. So yeah, this V over sigma distribution is rather similar, right? And I don't know what it means in context of the sigma 1 contrast between the two, but the fact that you have a high sigma 1 and a large Sirzik index does not mean you don't rotate, right? It's a very obvious empirical statement. In fact, the color coding is the velocity at RE, and the darkest point, they're all quiescent. If you take the 10 fastest rotating galaxies in LEGA-C, they're all quiescent because they're compact, right? So you get these fast spinning disks. The uncertainties are large, right? And that's because in this model I mentioned, we don't have a mass follows light assumption. Our data go out too far, so your dark matter dominated pretty quickly. So we have an NFW component in there on top of the stellar light profile. And of course that's very uncertain. We just basically marginalize in most cases over that prior parameter space. That's why the uncertainties are large and probably realistic. So we use this to calibrate our virial mass estimates. There's an inclination correction in our virial mass estimates of the kind of sigma squared r. No time to talk about that. What I do want to mention is that if you look at the V over sigma of the quiescent galaxies in LEGA-C, this is now an observed quantity. The dynamical model is gone now because this was 4 years ago. It was first look paper. This is just empirically measured V over sigma in some way. Ask me if you want to know. And we compare it with quality downgraded Khalifa V over sigmas. And we take your beautiful data cube and you convolve it with 8 kiloparsec C-ing, put a giant slit on it, and measure V over sigma in the same way as we do. And we see a whole lot more rotation at redshift 0.8 than at redshift 0 in the quiescent galaxies. So they slow down by a lot. And this, for me, this adds to the picture that we've created from the size evolution, that these galaxies grow in size through dissipation as merging. It fits in. This is probably the most direct evidence for that picture. does it happen in the simulations? It's a lot of simulation people here, so I thought I would tell you a little bit about what we're doing there. So that's the last topic. These are TNG. These are stellar velocity maps from TNG snapshots of legacy-like galaxies. Passive galaxies are redshift 0.8. We put these halos edge on. We just make the velocity fields as they come from the particle data. And that's very qualitatively. The vast majority look like that. A lot of rotation. At redshift 0, of a similarly selected sample, you see kind of the same. It's different, but the same. There's a lot of rotation in most galaxies. Now, of course, to make quantitative sense of this, we need to take these beautiful TNG data and make them as horrible looking as the legacy kinematic data cubes by convolving them, putting our slit and our spatial elements on top of it, and extract kinematic information in exact the same way as we did for legacy. And this is where this story stops. I don't have an answer for you. Does V over sigma evolve the same way in TNG or not? We simply don't know yet. We're working on it. I'll get to who this is doing in a second. Because there's one other element that we've added to the question. Here's the equivalent of what I just showed, but then simulating for a different simulation, LEGA. So that's L-star star-forming galaxies, if you recall. And here we simulate not legacy data at redshift 0.8, but SAMI data at redshift low. Right? So the entire data cube is in here. Every stellar particle gets its high resolution template. You integrate an entire data cube along the line of sight. You extract and measure the kinematic information just like in the observations with noise and whatnot. Now, other people have done this. What we have added, full radiated transfer of every spectral resolution element across the spectrum. So you get dramatic changes in the stellar kinematic picture. Right here, everything looks okay. You see this interesting ring-like structure in the velocity dispersion map, that's entirely gone. The velocities are way down. This disk is inclined by 72 degrees, by the way, so of course it's understandable you get in trouble there. The only reason I'm showing this is what we've been working on. This is led by a PhD student in Ghent. I'm working on this together with Maarten Baas. And if you know that name, it's because he created the SCURT radiative transfer code that they're using in Eagle and TNG these days. And it's sort of a hybrid effort between the legacy team, the SAMI team, because funding streams. Just to tell you that we're, I think we're the only ones who have done this, full radiative transfer, high resolution data cubes. And with that, I'll end, put on some takeaway messages, and I'll take questions. Thank you.
All right, thank you very much. Questions for Arjen? I'll start over here.
Hi. So I was a bit surprised at your plot of specific star formation rate versus sigma 1. It seemed from the plot that the value at which you got quenched galaxies was 10.5. I'm used to seeing that drop off as like 9.5, like an order of magnitude below what you had on your vertical axis. Now there was no units on your plot, so I'm not sure if this is the reason why.
Oh.
So I guess in units of solar masses per square KPC, I'm used to seeing that quench drop at around 9.5, and I see it at around 10.5 on your plot. So I'm wondering if this is correct or.
This is total mass within 1 kiloparsec, solar masses. Log sigma. Sorry, this. Yeah. Does that make sense to you, or do you think it should?
Well, I'm just surprised about the numerical value. I'm used to seeing it 10 times smaller than that. So I'm wondering if you can clarify for me why I might have this mistaken impression for what.
Oh, this is the number that's in all the papers. I think all the observational papers are somewhere around here. It depends a little bit. These are prospector-based masses, which are up to 0.2 dex higher than the masses we've been using in the past. So I guess you can move it here. That's kind of the.
Okay, we had another question here, I think, and then Sandy after that.
Thank you for the very nice talk, Arjen. I was wondering at your view over sigma plot versus mass. There are some slow rotators at low masses. So the general picture in the local universe is that below a given mass you don't have slow rotators. So I wonder if you've looked at those and what do they look like? I think for the local universe works, it starts really at 10 to 11 or something like that. Yeah.
So one thing, this is dynamical mass. If you plot stellar mass here, there's sort of a, because the RE is in here, right? So that changes the picture a little bit. But you're right, there are relatively low mass non-rotating galaxies. Some are very flat. So that reminds me of this galaxy NGC 4550, which has 2 counter-rotating disks. I'm not saying that they're all like that. There's also probably round compact things. But if they're very small, we can't really resolve anything anymore, right? And we'd have to look at the individual error bars on this thing. That's the median error bar. And I wouldn't be surprised if a handful of these things have error bars that are this big, and this is just the corner of the posterior. Things. But you're right, it's interesting enough to take a look at all of them, see what's going on, if it's the data or the posterior or something.
I'd like to make a remark about sigma 1.
Yes.
Actually, when it was first discovered, in the next sentence, it was said that it was a necessary but not sufficient condition. This has been with us since the very beginning. So I'm delighted to think that maybe switching to a different radius would spread things out a bit more, but
the projection, right? That's
the G project
splits it.
But I do think that, at least in local galaxies, there are objects of the same Sirsic index, which might not respond to a change in 3D radius. And so locally, we might be left with some contradictions. I don't know that it'll solve the whole problem.
Okay, so we should move to the next talk. Let's thank Arjen again.